Thank you. First of all, I'd like to thank the organizers and the University of Utah really for this wonderful opportunity to share my story with you. What I'm going to talk to you about really is my research interests and how I hope to play my small part in completing the loop from laboratory discoveries into new treatments for cancer. So a little bit about me. I was born in Malaysia, a little country in Southeast Asia, and there it is blown up here. Capital city Kuala Lumpur is probably the most famous for its twin towers. At one point, the tallest buildings in the world. But for me, when I grew up close to Kuala Lumpur, life was really all about family and quite a lot of fun exploring some wild, crazy places. And this is a picture we took in a trip to the national park. And here's another picture of a trip with some friends. We got a guy with a boat, and he just took us to random beautiful islands. And so those were really, really beautiful, fun memories for me. It was really my love of the outdoors and of nature that persuaded me to pursue a degree in the life sciences. And there I went all the way to the University of Manchester in the heart of England. Really, at the time, there was no internet, and it just seemed like a good place, and I had the opportunity to go there. And so this was the fabulous campus of Manchester University. A beautiful sunny day, red brick campus, really pure English experience. But little did I know that I was going to spend 7.5 years doing this. So Manchester is really known as the rain capital of the north. I mean, I lived in Malaysia, I didn't know anything. So this is where it was a great place to be a student, but really I spent most of my time pursuing more indoor activities. So this was my time as a one-year internship at a small pharmaceutical company that I became exposed to the notion of cancer research as a career. Also, as for many in the audience, I assume cancer is highly personal for me. My maternal grandmother had 11 children, which was rare even at the time. And this is my mother, a glamorous lady over there, and she's a brave cancer survivor, as is her sister next to her. But 3 of her siblings we have lost to cancer. And so we cherish the time we have, but really cancer has cast a long shadow in my family. And so I felt privileged to pursue a career that might make a difference to those around me. So this is not a political statement. This is an analogy of normal tissue and how I want to explain what cancer really is. So normal tissue, I say a brick wall, is comprised of bricks that have an ordered structure that enable a wall to function. And similarly, in normal tissues, we have cells, and the cells have to be a certain size, a certain shape, and a certain position in order for the whole tissue to function properly. And this is governed really by a set of signals that tell cells to grow and stop growing, and if they don't do what they're supposed to commit suicide. So in 2010, a seminal paper was published describing the hallmarks of cancer. So this defines what cancer is. And really, it's a cancer's break away from these control mechanisms. So these cells grow even though there are no growth signals. They keep growing even though the signals tell them to stop growing. And when the body says, hey, kill yourself because you're not doing what you're supposed to, they don't do that either. Instead, they actually grow their own blood supply, spread and metastasize throughout the tissue, and they're immortal. They keep dividing and keep growing. So you might find a very complex disease like cancer as something quite simple as the changes that happen that fuel a cancer struggle, a cell struggle for independence. It wants to break free from the rules that it has to follow. So my research is really focused on the notion of hypoxia, low oxygen as a driver of solid tumors. So if you think of a solid tumor and its architecture, you can imagine that cells furthest from the blood vessels suffer from lower oxygen tension. And interestingly, low oxygen tension actually changes the behavior of these cells and makes them more aggressive and makes tumors more likely to kill the patients. And if you look at the consequences of hypoxia, really you find that they're really all the hallmarks of cancer. So if we could target tumor hypoxia in some way, we could really address all the hallmarks that make cancer a cancer and make it deadly. And what is known about hypoxia is the response to hypoxia is driven by what is known as the hypoxia-inducible factors, the HIFs. These are transcription factors, and what these do is that they turn on a large number of genes important for the response to hypoxia. In this case, the HIFs turn on the transcription of hundreds, if not thousands, of genes required for tumors to survive hypoxia. And so HIFs are activated under low oxygen. And so during my research, I asked a question: could we really target hypoxic tumors, for example, by targeting the HIFs, and therefore address all the hallmarks of cancer? This research has taken me on a journey really from rainy Manchester. I had enough of that. So I did my postdoctoral training at Tucson, Arizona. And then on to the MD Anderson Cancer Center and the SBP Medical Discovery Institute in La Jolla. I joined the University of Utah in June of 2007, and it has been a really great experience for me. The camaraderie, mentorship, and collaborative environment has been really a great experience for me, and Salt Lake City is quite a nice, beautiful, crazy place. It snows more than I was ever used to. But my research has coalesced on the study of kidney cancer and the study of the HIFs. And why that is because, like I mentioned before, the hypoxia-inducible factors HIF really drive the response to hypoxia, and HIF2 is highly expressed in kidney cancer. In normal tissue, a novel protein, von Hippel-Lindau tumor suppressor protein, turns the HIFs off. But in kidney cancer, for some reason, this gene is lost. So 90% of kidney cancer patients do not have the VHL protein, and therefore the HIF goes crazy and drives all these outcomes that promote tumor progression. And these are somewhat addressed by current therapies. But really, the main thing that kills most patients is metastasis, and that is not addressed by current therapies. And what I was thinking was that, wouldn't it be cool if we could just directly target HIF? That would be the major factor that drives everything, and that would make things better for patients. And my research has focused on themes such as these: identifying novel therapeutic targets in hypoxic tumors that we can target to make patients' lives better. However, one of the main issues with cancer research is the translation of basic science research into new therapies that actually benefit patients. So I've been fortunate to be funded by 2 National Cancer Institute grants totaling $3.1 million. But I was frustrated because I knew that these new therapies or new targets I was finding was not going to be translated to anything, at least anytime soon. So the average time of translation of basic science research to new therapies is about 20 years. And the reason for this is somewhat straightforward. Drug discovery and drug development is very expensive. And drug companies, when they want to put their money on something, they put their money on something they believe is proven and safe. So a new therapeutic target really is something risky for a drug company, and they might not even know whether this target is real because Mei Koh talked about it. I mean, so you know, you need a bit more than that to invest in a new drug development plan. And so I sought my own funding, and I was lucky this year to receive a small business innovation grant from the National Cancer Institute to found my own little biotech company that can develop these novel therapeutic targets. So the company is called Kuda Therapeutics, and our aim was really to translate these discoveries, validate and de-risk them so we can rapidly translate these strategies to the clinic. So where are we now? You've seen this slide before. So we know that HIF2 is a major driver of kidney cancer progression, and we know that current therapies are inadequate. We have now identified a novel inhibitor that can selectively and directly target HIF2 alpha. As an additive effect, we found that this molecule also targets tumor iron metabolism that contributes to a tumor's ability to metastasize and proliferate, and so we can actually target 2 drivers of kidney cancer. We believe that this has the potential to really transform and improve the outcome of patients with kidney cancer. So I hope and aim through my efforts through the University of Utah and Kuda Therapeutics to rapidly translate these novel therapies such as this to improve the treatment options of patients with cancer. So thank you for your attention. I'll take questions.